All right, so we're going to talk about directional control valves. Y'all have already worked a little bit with them in labs, but we're going to talk about them in depth. Y'all have to excuse me, I'm a little stuffy right now. Allergies and the yellow pollen death cloud outside are killing me right now. Oh, it doesn't matter. Flonase doesn't work for me. I'm on.
I'm taking everything right now.
Like I said, you'll have to excuse me if I'm coughing every now and then and stuff. My sinuses are. Oh. Yeah, and we're still dealing with COVID, so everybody hang on to that. So directional control valves. Excuse me. Good gosh. These direct fluid flow to start, stop, or reverse direction of motion of the fluid, cylinders, motors, and other equipment. Yeah, I hate this tummy. So these can be operated manually, automatically by mechanical devices, with electrical signals, with compressed air, hydraulic power. There's a lot of different ways to, excuse me, to operate these. Excuse me. Strangling on something here. Won't help. I just gotta cough it up. All right, so first of all, we talk about the number of ports in each valve. These are also also known as the number of ways. They have between 2 to 5 ports or ways per valve. With the fifth port generally being an exhaust port. There's about 2 or 3 control positions. There can also be a single one, if that is a pressure relief valve. And they have, excuse me, I think I finally coughed it up. 2 or 3 ways that are usually 2 position, 4 to 5 are generally a 3 position. That is not a hard and fast rule. You can have a 4 port or a 5 port 2 position. These are actually very common. And then you have the different types of control elements. You have things like poppet, spool, or disc. We'll talk about each of those as we go through. As for the method of operation. So this is how we identify them as the full breakdown. You start off with how many ports are there. And generally, like I said, there's between 2 to 5 ports. Okay? You have to have between 2 to 5 ports, and those are known as the ways. The number of positions, then you don't really talk about the control elements as much when you're describing that, but you do talk about the method of operation. I'll give you an example. You actually have a few of these different ports on the wall here. If I tell you I'm looking for a 2-position 5-way valve, and yes, those do exist, yes, you will use them in lab, then you're looking for a valve that has 2 positions and 5 ports. Now, those 5 ports may not all be visible. 2 of them might just be exhaust ports. So that is why you have a 2-5. And the next thing you would tell somebody is it manually operated, electrically operated, mechanically operated? And the third thing you might tell them is, does it have a spring to return it to its central position? So we describe these very, very carefully because the way you describe them and what you have to tell people to describe them tells you what kind of valve you're dealing with. And it can also clue you in as to what kind of fluid power you're dealing with. Are you dealing with a hydraulic system or a pneumatic system? And our great work study, James has actually found a bunch of valves and things like that that are scattered around the room now that y'all can look at whenever we take a break. You can actually lay hands on them. I would pass them around, but I'm afraid somebody would probably drop it on them on their hand or something. They're quite heavy. All right, so some of the different valves we have these are the manually operated valves, guys. So these are something that you would lay hands on to deal with. So you have things like gate valves, which basically are exactly what they sound like. They're a gate. You have globe valves, needle valves, plug valves, and ball valves. Okay. So we've got a gate valve. There we go. So down here are the two gate valves. Okay. So they act just like a gate. When you spin them around up here, since it's manually operated, you're going to be spinning something or you're moving something. It's just like your faucet or at home, your water spigot, right? As you move it up, the gate opens so that water can move through. And then you close it down to make it shut. All of these operate very similarly to that. The ball valve, well, you'll see how it works here in just a minute. Some of these can be operated by opening them a little bit and they're not damaged. Some of them, you do not want to do that. Why? Because it can actually physically damage the valve itself to try and crack it and leave it cracked. So think about your spigot at home when you're dealing with your garden hose. Sometimes you decide that you don't want a full flow, right? So you just kind of crack it open just enough that you get like a trickle of water out, or maybe half pressure. Now, think about the fact that you're dealing with a hydraulic fluid. You're dealing with something that has massive amounts of pressure to put behind it. Okay, so you have massive amounts of pressure behind this valve. What can that potentially do to the valve itself? Weaken it, rupture it. It can cause it to break down over time. If you've ever dealt with a really old garden spigot that's been used for 20 years or better, do they work as efficiently or as well as they used to? No, they've started to what? Corrode, break down, but worst of all, they've started to leak, right? They no longer seal completely, they leak. And that's what I mean, is you can't, on some of these valves, you cannot just crack it open a little bit. You're going to cause it to deteriorate faster, and eventually it's going to leak. Some valves can be guaranteed for 20 years under certain conditions, but the second you start trying to make it do things it's not supposed to do, that's when you're going to start having issues with it. Just like anything else in the world. So you have a globe valve. You can actually see it working if I can get my mouse over there. There we go. So you have the valve right here that to open it, it pulls up and allows flow through. You have a basic gate valve over here, You can see raises and lowers. You have your butterfly valve, and you have a plug valve over on this side. Fluid. No. Most of the manual valves seal tight. If it was something like a pressure relief valve, yes, that's what it would do. Is the second that pressure got too much, and that was a pressure relief valve, it would raise itself up and allow the flow to go through. For the most part, we use pressure relief valves at the very beginning of a system, or we use it next to something that might be a little more delicate and end up with a back pressure. Yeah, that's one of the valves right there that y'all can mess with. Gate valve that he's demonstrating right there. So with pressure relief valve, we tend to put those with mechanicals or hydraulics, pneumatics that can be damaged by excessive pressure. Or if we know that we're going to have to hold pressure somewhere, but if we have pressure that's going to back up in the system, we need to dump it elsewhere. Sort of like a dam on a river, right? You have channels cut to either side of the dam to allow water release if there's too much water backed up. Let's say there's a giant storm upstream and it's slamming a bunch of water down into the dam. Dam can only hold so much pressure back, so it can open these gates to either side that allow that water through and allows the water to pass downstream harmlessly. I'm trying to talk too fast. So that's what you're talking about as far as pressure relief. Okay. For all of these are supposed to be manually operated. So in other words, you as the person have to go in and open the valve or close the valve as necessary. If that makes any sense whatsoever. So what you're seeing is somebody comes in and opens the valve, the fluid just moves through. It's just showing you how the fluid moves through as it goes through, as it passes through that particular valve. So you have your gate valve, you have your globe valve, needle valve, plug valve, ball valve. These are just the most common ones out there. I'll talk a little bit more about them here in a minute. Ones that are automatically operated. So all valves are operated several different ways. It depends upon your system and how much control an operator needs to have on the system. So why would an operator need control of a system? Let me put it to you that way. Something goes wrong and you need to take control back. This is one of the biggest ones I can think of. You know, some sort of havoc is being caused somewhere else, so thus somebody's got to step in, take control, and make sure that nobody's getting hurt downstream on the production line. So manual operation is not seen with a lot of automation, unless it's certain places where somebody needs to make sure that everything is moving smoothly, where you have to have somebody be able to go in and shut off things so that work can be done elsewhere. Okay. Self-actuated has become a really big thing, especially with automation, because that way you don't have to have somebody sitting there waiting to push a button. The button is pushed on its own by pressure. The system can create its own pressure into that system, thus doing everything from afar. You can have mechanically operated. We'll look at some of the different labs with those. Electric solenoids, those are actually a really awesome one too. So you have an electric current going to certain parts that they basically the solenoid flexes as the electrical current is run through it. And then you have pneumatic pressure, hydraulic pressure, which are pilot operated or self-operated. I don't know why those are broken out from the second one, but there you go. You have a solenoid pilot, which is again an electric solenoid. I did not write some of these slides. These are ones I'm using. So if something like that happens, I'm sorry. Need to go back in and correct some of these. So this particular valve, okay, so let me kind of point something out to y'all. And that is, where is my mouse? There's my mouse. And that is this little box down here at the bottom. Now let me go ahead and say this. Whenever you see any valve, okay, this is for every valve out there. The very base thing you will start off with is a little box. In this case, we're starting off with two little boxes. Now, what these two boxes means is that it has two different positions. Okay? It has a position A and a position B. Okay? It has a position A and it has a position B. Or position 1, position 2, whatever you want to call it. In this case, it would actually be position 1 and 2. So how do I tell position 1 from position 2? What do y'all think? How do I tell the origin position, I guess you could call it, versus the secondary position? You're close. It's this part right here. You see how these are sticking out of the box? That means that my pipes go directly to these two places right here. Another way you can tell is generally you'll have a 1 and a 2. And what those mean are ports 1 and port 2. Okay? So this particular valve is a normally closed valve. We don't know how it's actuated yet because we're not told. All we know is we have two positions and two ways. So this right here is what they're calling a 2-2. Just to, go ahead. Two positions, two ways. Remember, what is a way? Way is how many ports are there? How many ways do I get fluid into and out of this valve? Okay? That's why this is a 2-2. Two positions, two ports. Or two positions, two ways. This is the most common way that it's going to be called. Does it make sense? I'm trying to do this as we go along so we don't end up with a crash course on why this isn't the way it is later. Okay? In particular one, this one they're talking about is a solenoid operated. So how many of you have your little books out? Your little $1.75 books. Y'all got them yet? All right. you do not have them, raise your hand real quick and I'll let you borrow one. Oh, you don't want my ragamuffin looking one. All right, so looking down at the bottom of page 3, you start looking and seeing all the different types of cylinders. You'll see what I'm talking about? Page 3, so right inside the front cover. If you turn that page to page 4 and look at the very top, these are the different types of actuation. Okay? You might want to make note of that, guys. So on page 3 is the different valves. On page 4 are the different actuations of the valves, as well as some irregular valves that we'll be dealing with. We'll talk more about those at another time. Okay. Mhm. No, it'd be a normally closed. Yes, you're right. It is normally open. I'm sorry. I'm trying to do. No. That is a normally closed because it's opposite of electricity. Electricity, if it's open, that means there is no flow. In this case, it's closed, like closing a door. So if you look at the very first one, two-way normally closed to position, and look at the one on the screen. Okay, what you're looking for, again, are the places where it sticks out of the box. So open, this one is, see how that's, yep. So this is a normally closed tube 2. And the reason so the difference between a closed valve and an open valve is just like a closed door versus an open door. If you close the door, nothing gets in. Open the door, you can let anything through, right? Does that make sense? Versus electricity, where if it's open, there's nothing getting through. If it's closed, everything gets through, right? So those of you that have had electricity 101, it's a little different. It's the opposite, actually. Does that make a little more sense? All right. All right, so the ones they have here are solenoids. What is a solenoid? Those of you that have gone a little further in electrical. Okay, for those of you that need a refresher, a solenoid takes an electric current on a metal rod and is able to move the metal back and forth after varying the current, if I can talk. So it varies the current with electrical current. I'm sorry, it varies opening with its electrical current. I can say it right. Does it make a little more sense? So a solenoid is going to vary its position depending upon electrical current. Okay? If you look right here at our solenoid diagram, you can see the metal rod, you see the coils of wire. So as it runs a current through it, the solenoid's going to move. Okay? So it varies its position with that electrical current. Does that make sense? All right. So one of the biggest things we use are what are called check valves. Check valves are probably one of the most important things. The very basic symbol for a check valve is this guy right here. Now then, in electrical, what is a one-way valve? What is a one-way, what allows current flow in one way? There is a singular device in electrical that allows flow of electricity in one direction. Oh God. It is a diode. In other words, one of those little things that can light up, but generally it just allows for flow in one direction. It filters out signals from the opposite direction. I figure y'all might have had some contact with that. A flow control valve is the exact same thing. It allows flow in one direction. This is a check valve, guys. So what this does is that if you put flow in the correct direction, flow goes through. If you try and reverse flow, it stops it cold. It shoves that ball back into its socket, and you aren't going to remove it the other way. And it's not just a ball, it can be, excuse me. It can be anything. As long as it turns itself back into its socket, it can stop the flow in the opposite direction. Now, why would we want that? How many of y'all live with a house that's below grade and connected to sewer? So one of the biggest things you have, one of the biggest problems you can have with sewer is what's called what? Anybody know? Backflow. It is nasty. That's where the sewer basically backs up into your house. It's not pretty. It's not nice. It's not good. It stinks. Yeah, because you don't know what's coming back in that. So it's not a pleasant thing to have happen. All right. So what you have with check valves is a way to prevent backflow. It allows flow in one direction, not the other, so you don't end up with back pressure or backflow that might harm your lines back upstream. Does that make sense? You want everything to continue flowing downstream. You don't want it backing up upstream because that can cause damage to whatever is upstream. But we also have other ways we use it, and we'll talk about those here in a minute. One of the biggest ways we use it is what are called flow control valves. We'll get into those here in a minute. So they allow flow in one direction. You have ones that use a flapper, ones that use balls, poppets. But in order to move that ball or that poppet enough to allow flow, because essentially what these have are springs behind them, is what's called cracking pressure. So how much pressure do you need to obtain to move this back enough that you can allow flow? Okay? Basically, how much pressure does it take to hold the door open? So another way you can think of it is kind of like these doors over here. You can open them one way, you can't open them the other, right? If you try and open them the other way, you're going to hit a wall, which could be entertaining. But let's not do that. So cracking pressure, how much pressure does it take to hold that open, to move it in the first place and then hold it? Does that make sense? So how do I know that I've got my flow control valve facing the right way? You've got to pay attention to this guy right here. Because which way this faces is going to tell you which way that pressure's got to go. Because if I try and put pressure the wrong way, what's going to happen? Nada. You close it off. Okay. So here's some different check valves. As you can see, flow goes one way, it does not go the other. Okay. Flow goes one way, it cannot go the other. Does it make sense, guys? Kind of like the valves on your heart are supposed to do, right? You allow flow one direction, not the other. All of these are check valves. If you notice, all of them are allowing flow in only one direction. So for this one, if you notice, whenever it starts pushing pressure back on this particular one, it closes this valve. Whenever this one starts sucking pressure back this way, it closes that valve. So yes, the second you start applying the second you apply back pressure or put pressure the wrong way on these, it closes it off. You're not going to get it to move. Yes. Okay. All right. So spring return. So a lot of valves use springs. Why? Because we don't want our things to be kept in the same position ad nauseum. Having a spring, being able to push it back into its original position, works well for what we need it to do. Does that make sense? So you have the pressure of a spring that's going to hold things closed or hold them in the position. The lowest pressure that will open this valve against the spring is the cracking pressure. It prevents air from flowing back into the compressor, or it can prevent, I said, fluid flow in the wrong direction can cause all sorts of havoc. Think about just your circulatory system. What happens if fluid flows the wrong way in your circulatory system? You can bust a vein, right? Bust an artery. Bad things happen. That's the same for most fluid power systems, guys. If you start backing up the wrong way, you're gonna have havoc. Think about if, I'll just leave it at that. Leave it to the imagination. Now then, taking a look at this, first of all, which ones are facing the right way? You sure? It's the bottom one. Why is the bottom one correct? Well, because this is where my pressure's coming from. These nice little compressors. Where is my pressure not coming from? It's from tank, which is what this is. Okay, so you gotta make sure where your compressor is, which way it's facing. So what would be my minimal cracking pressure? Excuse me. So let's say this is 5 psi. This is 10 psi. And we'll say this is 15 psi. What is the minimum amount of pressure I've got to have to get my fluid from my compressor to, or not my compressor, from my pump to my tank? It'd be a minimum of 15 psi. That will guarantee me flow through the whole system. Does that make sense? Yes. You need a minimum of 15 to, you can have more than that, but you need to have a minimum of 15 psi. 15 to 30, I would say. All right, so part 2 of this. Which ones are facing the right way? That one right there, right? Putting it at the top corner of it. So yes. So what minimum cracking pressure do I need to get my fluid from my compressor to my, excuse me, I keep saying compressor, I mean pump. To get it from my pump to my tank. I need even less than that. I only need 5. It's in parallel. So all you need is the minimum to get at least one of these valves open and you're good to go. Can you use more than that? Yes. It needs to go to the one with the lowest pressure. Does that make sense? All right. So before we get to self-actuated valves, let's take about a 10-minute break. Give y'all a minute to catch your breath. So shuttle valves or self-actuated valves, there's a couple of different types of these. One of the common ones is a shuttle valve, which is a very similar to check valves with usually 3 or 4 ways. Which what is a way? It's a port. How many ports are you dealing with? This can allow for reverse flow, but only in certain directions. That's why it's different than a check valve. Sorry. So here's one right here. I don't know if it's, there goes the animation. So what this guy does is he allows flow from one direction or the other. What do you think would happen if I tried to apply pressure from both directions? Well, you might blow a seal, but at the very most, or you would probably end up just shutting off your valve. Well, we'll actually be playing with these, but essentially what this another word for this, I don't know if you've ever heard of OR logic. Or what is OR logic? This or that, left or right. So essentially what I can do is I can have two push buttons controlling the same thing. So I can have a remote push button here and a remote push button here, and they control the same valve. They control the same cylinder. Does that make sense? Well, redundancy is not exactly terrible to have. In this case, if I actually tried to apply pressure from both ends, it would stop the valve in the center and you would not get flow at all. It's one of the weird things that would happen with this. If this pressure was the same. Otherwise, the stronger pressure will push through. This is a shuttle valve, which is quite an interesting valve. It uses the principles of a check valve, but allows for OR logic. Does that make sense? So control valve elements. So one of the other ways we do this is what are the control elements? This is how you would identify it in a way to buy it. It's not something you usually use to identify it when you're they're actually in use. Put it that way. So you have the spool valve, which is the spool element, which is one of the most common. You have the poppet, you have reciprocating disc, and you have rotary. But the essentials of this is how are your passages aligned for flow? That's the biggest thing about this. How is the passageway set up for flow? So if you look down here at the very bottom, you notice you have, this is a 3 position, how many ports or how many ways? Look very closely. How many ways have I got on this? A total of 4. And I'll show you why. So I've got one coming from the compressor all the way to whatever this is going to. Change ink real quick. And then I've got this guy coming through this way. So it goes from the valve to the receiver. So this is position 1 with 4 ways. Position 2 is a neutral. So in other words, my receiver is receiving pressure from my valve, but my pressure and my compressor is going to my valve. I'm sorry. So this is position 2, which is the other extreme. Back up on that one. It's the secondary extreme of this. Then the third one is where everything is closed off. So everything's going to hold pressure with this. This is a neutral position. Generally, B and C would be reversed in the way you would look at it. So just like in your book, you can have a 3-position, 4-way, and it's going to depend upon which part of this is going where. Make sense? So this is a 2-2, and they're showing you with a spool valve. So this one is manually operated with a spring return. How do I know it's spring return? Because this right here is the symbol for a spring. All right, so how do I know it's normally open? Because this arrow is longer. It goes all the way through. It's telling me this is my normal position of actuation. This will close itself off whenever I press the button. Okay? Does that make sense? Now, how would I tell if it's a hydraulic or a pneumatic valve? Those right there. If it's clear, it's an air. If it's colored, it's hydraulic. Clear is pneumatic, filled in is hydraulic. Okay? Fastest, easiest way to tell. Another way to tell is if it gets this symbol. That's a symbol for tank. Anytime you see a little inverted T like that, you're going to tank. You're going to have some sort of a reservoir somewhere that fluid has to return to. So just like in your car, what do you have in your car? You have an oil reservoir, right? What does that oil reservoir do? It holds the oil for your car so that when your car needs the oil, it can pull from it, but it also returns to it, because otherwise we'd be squirting oil all over the roads and it'd be a nasty mess and very expensive. Correct? All right, so real quick, how many so this is a, excuse me, how many ways does this have? How many positions? Well, technically, this one actually has 3. I don't know why they're calling it a 2-way, because it has a center position. So I'm not sure why they're calling it. Unless they're saying that it has to be pressed one way or the other. That's the only way I can see where that would be a 2 position. Otherwise, it would be normally be a 3. Yes, but the center position is what would be called a closed position. So basically, fluid would not flow in any direction; it'd all just be sitting. So that would be a neutral position, but that's still a position. So I think I need to go back in one day and correct this. I think that's actually a 3-way. Because a 3 position, I'm sorry, so that's a 3 position. How I know? Because here's a 3 position, another 3 position versus a 2 position. All right. So if we're trying to keep a load raised or lowered, okay, these are all using 3-position valves. I'm sorry, 3-way valves. Excuse me. 3 ways and 2 ways. Excuse me. So P is pressure. What do you think E stands for? E stands for exhaust. Okay. So for B, I have pressure coming in at P, but it's not able to go anywhere. All my pressure is being emptied to my exhaust. Y'all see that? Up here in the top corner. Where is my mouse? Okay, there it is. So I have pressure coming in at P, but it can't go anywhere because it's teed off. Do y'all see that? When it's teed off like that, it means there's no pressure through. It's a closed position. Does it make sense? What I do have is here's my cylinder, and all my pressure is going to my exhaust at this point. Does that make sense? So in other words, this is going to spring back. All that spring is putting pressure on the cylinder and moving the air to the exhaust. When I actuate this, my pressure will go through into this, and it will extend. Okay, I can lock it there and hold pressure on it. With pneumatics, I can do that for a very long, indefinitely time. This right here? Look in your book on page 4. Second one from the left on the very top row. And that's the symbol for a manual lever. Lever, lever, tomato, tomato, however you want to say it. I'm good with it. I'm not picky on how you say things. Okay? So for example C, the one here in the middle, there it is. So for example C here, here's my pressure. What is this the symbol for? What do y'all think? It's the symbol for a what? Symbol for a compressor. Is the symbol for a compressor. So this guy in his first actuation is applying pressure to B, causing this guy to extend. He is not applying pressure to C, but the pressure is locked in because of this little piece right here. Y'all see that? Now, in its second actuation, I do apply pressure to A because it switches to this box right here. This guy is not emptying any pressure out. Instead, he blocks it off. How do I relieve pressure on this system? If this guy is not emptying pressure, he has no exhaust ports whatsoever, how do I relieve pressure from this system? With these two guys right here. Because those are exhausting. Because they're in a normally closed position to start with, but they have the potential to be normally open. Okay? Their position starts normally closed, but when they're actuated, they move to being open. Y'all see that? Does that kind of make sense to y'all? Okay. Okay, so when the only way that these cylinders will retract is if you actuate this guy or this guy. These cylinders will not retract otherwise. They will extend and hold. They cannot relieve pressure any other way. Does it make sense? Okay. This particular one at the very bottom, for example, D, all it's doing is showing you that it's able to put a motor, and the motor will not stop spinning on this one actually, because you're adding pressure to both inputs. The only output is on the motor itself. It's got an exhaust. Now, how do I know that's a motor? Well, because it's a symbol for a motor, first of all. And specifically, this is a fixed displacement motor. Now, before we go too much further, I want to kind of explain the difference between a motor versus a compressor slash pump. Just to kind of clear this up, a motor, oh, that is a ruddy circle right there. All right. A motor, it takes air in or takes fluid in. A compressor or pump is going to push fluid or air out. It's all the way that triangle faces. Okay? Does that make sense? And just like with any other valve or anything, if it's colored in hydraulic, if it's clear, it's pneumatic. Just to go ahead and put that out there, since we're displaying a motor here, I figured I'd go ahead and put that out there as a way to go ahead and let y'all have that information. Okay? If it points inwards to the center of the symbol, you've got a motor. If it points outwards, it's a compressor or pump. All right? All right. I'm sorry. And then we have a couple of other ones. You have a 3-3 on these two down here at the bottom. They are 3 position, 3 ways. There's one with that. So you can see on the symbols themselves, P is for pressure, E is for exhaust. This one just has pressure, and then it has ports A and B. You can decide what ports A and B are as the person that installs it. You could very well make A an exhaust or B an exhaust, depending upon what you need to do. Okay? What now? A circle that, if you have a circle with a triangle pointing out, that's a pump or motor. I'm sorry, that's a pump or a compressor. If it points in, it's a motor. I don't have a motor up and running right now, or I'd show you why a motor takes air in. It's actually quite funny. And it makes a very funny noise. All right, so this one is a 4-way valve with this one actually does have 2 positions and only 2 positions because it does not have a spring to push it back, and its central position or its beginning position is the first position. So for this one, this actually is a 4-2, not like the other one which had 3 positions. Again, I'm going to have to go in and change that. Where is my... There it is. Sometimes finding the mouse from this angle is a bit hard. Yep, there it is. So I have an exhaust, I have a pressure, and then these would probably go to an actuator of some sort. That would run itself in and out. So in the first position, let me change ink color real quick. So in the first position, pressure comes in and it goes straight to B, which would cause my cylinder to retract. My air in the back end of this cylinder would exhaust out through port A and out to my exhaust. You'll see that? Now then, if I actuate it the other way, that means my pressure comes through here and it would go through A, causing my cylinder to extend. The air on this side would flow through B and out the exhaust. Actually go that way. Does that make sense, guys? A little bit more? All right. So here's another way to show you the same thing. So I've got pressure. Where's my little dot dot? There we go. Okay. Like I said, it's kind of hard to see it from this angle. I'm sorry. So if y'all see it and I can't, I'm sorry. It's kind of the way I'm having to work with this. So my pressure comes in through P, and in this first position, they've got it sent to B, which is retracting the cylinder. Which, by the way, which provides me more surface area and thus more force? Extending or retracting? Extending or retracting? It's extending. You get more force on extension. Why? Because you don't have to deal with this guy, the rod. Because the rod takes its own area inside that cylinder. Remember, everything likes to act to right angles. So if you've got something sitting right smack dab in the center, you can't move around it. Does that make sense? So that's why you get more force on extension than retraction. So the air behind here will come through A and go to its exhaust port. However, when I actuate it the other way, that means that my pressure will come in through my pressure valve, come out through A, and cause my cylinder to extend, All this air over here will come out through B and go through my exhaust. There's a reason I tell y'all to write in pencil. No, but this is just all this air that would be over here that was from whenever I forced this to retract. All this air has to go somewhere. We don't want it going around the seals of the rod. Instead, we put it through B to exhaust it back out. Does that make sense? All right, and then you've got this guy. Technically, he's a 4-position 3-way. No, he's not. Somebody put the wrong picture to that. Somebody really put the wrong picture to that. Never mind. That's actually a figure in your book. Okay, so what is a 3-position 5-way? Because there are 5 ports there. Somebody needs to check the book one day. The other one is a 3-position 4-way. I don't know off the top of my head. It's figure 211. Mm-hmm. So it's a 2-position, it's a 3-position 5-way since you have 5 ports. And then you have a 3-4 as the symbol for some reason. The actual symbol should have been this. All right, so the 3-4 is extremely common in hydraulics. You have a pressure and you have a tank, and then you have your 2 escape valves, I guess you could call them. 5-3s are extremely common in pneumatics. Why? Because it gives you more options for exhaust. Does that make sense? We like options to exhaust. 4-3s, or 3-4s, excuse me. Four threes, 4 ways, 3 positions, are very common in hydraulics. This would generally be your tank. You will not really see 5 positions used for, 5 ways used for this, simply because that would be a secondary tank line, and honestly, you're much more likely to want only one tank line. Keeps down the mess, keeps things simple, right? And what's the biggest rule we always like to use in anything we put together? Keep it simple, right? Because the more complex you make something, the more you're going to have what? More complexity, the more problems you're going to have. And that is true for anything you ever make. The more complex you make it, the more places you make to break it. How about that for a saying? The more complex you make it, the more places you make to break it. The more places you can break it. I mean, there are so many things that they've made overly complex these days. It's just astounding. One I can think of is the new tailgate on, I think it's a Ford or a Chevy truck. Like 6 positions for the way to put the tailgate down. Yeah, more places you can make to break it, right? Don't you love engineers? I sat on it. Didn't know that was something else. Yeah, pretty much. All right, so schematic symbols for a five-way valve. Again, you're going to generally with these have two exhaust ports. Excuse me. Here's some base symbols for y'all to kind of look over. How do I tell something's normally open versus normally closed? It's going to depend upon port 1. Always look for where it says the number 1 because that is port 1. That is your pressure port. Okay? What do y'all notice about the way they number these? Start from the bottom. Port 1 is your pressure port. Ports 3 and 5 are your exhaust ports. In pneumatics, you really don't always get to those exhaust ports. With ports 1, you can always access it. That's where you bring your pressure in. What are ports 2 and 4? What are ports 2 and 4 for? What do y'all think? Ports 2 and 4 are your useful ports, I guess you could say. That's where your pressure comes out of your valve. Those are your outputs. Thank you. For some reason, I couldn't think of that word. So 2 and 4 are outputs. 1 is your input. Three and 5 are exhaust or tank. 2 and 4 are your outputs. 1 is your input or pressure. Those are hard and fast rules just about. Now, could you technically put pressure in at 5 and 3? Yes, if you have access to them, you can. The ones that y'all will be dealing with in lab, you cannot access ports 3 and 5. They're exhaust ports and they're hidden. Now, there are some units that you can get access to those, so you could theoretically use those, but 99% of the time you'll use them as exhaust ports. If you're dealing with pneumatics, if you're dealing with hydraulics, they're tank ports. Okay? But the very biggest thing is that 1 will always be your pressure port. I don't care if you're dealing with hydraulics or pneumatics. 1 is your pressure. 2 and 4 are your outputs. Okay? I don't care what the symbol looks like. 2 and 4 are your outputs. 1 is your input. Okay? Everybody good? All right. We're going to go through this page real quick, and then I'm going to let y'all take another break. All right, so the biggest thing on this page you need to pay attention to is this set right here, this whole line, because this line is telling you everything you need to know about your pressure unit and exactly how your pressure unit works. By the way, these symbols are on page 4 at the very bottom. All right, the first thing you see should be your pressure gauge on the top one. Do you always have a pressure gauge? No, it might be totally separate from your service unit. That's going to depend upon the manufacturer and the specs of the engineer. Okay? Things you will always have. You always have an air or oil filter. You should always have a filter of some sort. And you should probably change it out fairly regularly. Why? Because just like the air filter in your house, what happens if you don't change it regularly? Well, it gets nasty, but what else does it do? It'll tear up your home air system, won't it? You don't clean that thing religiously. I think you're supposed to change filters every, what, 3 months? At least. If you have months like this where you have the yellow pollen death cloud, you probably should change it more frequently. Just to put that out there. Keeps the pollen out of your house. And that's the same thing for whenever you're using it for a plant, right? If you're using it for a manufacturing plant, you probably need to make sure you check the conditions of your filter quite regularly. Otherwise, it's going to get nasty. It's going to break down on you. The biggest problem you're going to have is it will start to run continuously. Why? Because it's just like a smoker, it's trying to pull air into a bunch of dirty lungs, right? Because your lungs filter the air that goes into your body. Or just like when your nose is congested and you're trying to pull air in through your nose, it becomes a lot harder. You find yourself short of breath. Your compressor does the same thing. It's trying to pull air in through this dirty filter, and if it can't do that, you're going to have it running continuously, right? So one of the biggest things you'll have is some sort of filter. With airlines, we also like to put in what we like to call the lubricator. Why? Because dry air is not actually that great for components. Any lubrication that's already on it and by the factory can dry out, it gets gunky, and that's a problem. But then there's also the fact that dry air means that you're going to run into a lot of what? A lot of friction, right? Because the drier it is, how much easier is it to get friction on dry air versus on wet air? That friction builds up a lot faster and a lot hotter, a lot sooner. Okay? So lubricators are a part of a lot of these. You will always have some form of a regulator on all of these. Why? Because we like to regulate our pressure. We don't want, 100 psi on something that only needs 20. Just to put that out there. Excuse me. And then one of the other things they have are things like mist separators. Those are not, I won't say they're not common, but they are not imperative. Put it that way. Your most likely things you're going to see are lubricators, regulators, lubricators, regulators, and filters, along with a pressure gauge of some sort. All right, y'all got any questions on that? Okay. So before we get to operators, we're going to take. So operators come as many and as differently as you can imagine. Because why do we need operators? We need something that's convenient for somebody to be able to use on a regular basis and gives them control of the cylinder, right? So we have everything from manuals like hand levers, buttons, foot pedals, things like that. Mechanical operators, which are the cams. So those that you saw in your drawer that have the little metal arm to it that you can push up and down, those are a cam operated. Okay? So why would you use a cam operated? Well, you can use it for something as simple as creating a counter. Think about it that way, right? If you put it on a roller, a box, why can't I not think of the name of it? A way that people unload boxes or load boxes and move boxes. What is it called? Conveyor, thank you. My brain could not come up with that word for some reason. If you put this with a conveyor, you can actually count what goes past it. It's a manual, I'm sorry, not a manual. It is a mechanical action and can be used as a sensor almost. Solenoids we've talked about, those require electricity. You got the spring, which you can use a spring one of two ways. If you have a single spring, excuse me, if you have a single spring as part of your symbol, that means you have what is likely called a spring return. Basically, once you push the button and you let it go, the spring forces it back. Does that make sense? If you have two springs, I will go ahead and tell you now, that is a 3-position valve, excuse me. That is a 3-position valve, and it will be what is called spring centered. Does that make sense? Because I can tell you now, that is a great test question. One spring means spring return. 2 springs means it's a 3-position valve, likely spring centered. Okay? 2 springs mean you are spring centered. We'll get to that here in just a second. All right, so the last one I want to really kind of point out, because pilot operated is something we'll talk about a little bit more here in a second, but a detent. So how many of y'all were looking that closely at the valves whenever you were taking inventory? Where you had the little one that had the selector switch. The selector switch has a detent operation to it. What that means is that when you push that switch and it locks in, it will not change position until you release it. That is what a detent is. And the way you can kind of really remember that is if you look at the detent, they have these little V's right here, these little grooves. That's meant to hold and grab something. Does that make sense? So kind of like a, well, I had an example, but I can't remember what the example is. So almost like a crossbow. Anybody ever seen a crossbow in the movies where they have to pull it back and they have that trigger? That trigger is what's holding that string back, right? Same thing for this. It's holding it into position until you are ready to release it. I'm sorry, that's the first thing that came to mind. One too many action movies. All right, so this is a different way to categorize all of them, but it's the same thing. You have manual control, um, lever control, um, mechanical control. You have a plunger versus a spring. The roller. You have solenoids, and then you have pilot valves or pressure control. So we'll get into a little bit more of this here in just a minute. So solenoid or pilot operated. All right. The whole thing about pilot operation is you don't want to be near this thing when it's being operated. You want to be out somewhere else. Okay. You want to be able to control it remotely. You might even make it just part of your assembly line that it just goes off when it goes off. Okay. You might tie it to sensors in an electrical circuit. You might tie it to the operation of one valve. Okay. Now it's going to operate the next valve in line. Okay. And again, with a solenoid, you have to have electricity to use this because the electrical will go across the windings and cause the solenoid to shift position. All right, so valve operators, the one at the very top corner with the black and the prongs. Where is the mouse? There it is. So this guy right here, number one, that is a double solenoid operated. How do I know? Because it's got plugs to it. And I can actually let y'all see that valve. It's over there on the table if you want to take a look at it in a minute. But those have to have those plug-in tie-ins for electrical circuit. You have your manual operator. That's this guy right here. That's a lever. You have a push button operation and cam operated. So basically the cam operated is looking for something to hit that arm. So if you put this as part of a conveyor belt and something comes along and taps it, it can be a counter or it can be used to operate another part of the circuit. Make sense? So all it's doing is looking for a tap on it or something to come press and hold, something to hit it. Yeah, it's a proximity sensor, just done with pneumatics or hydraulics. All right, this is a fun one. This is a pick and place feeding station. Okay. So if you look at this, first of all, I'm going to go ahead and tell you that these right here, you have these in lab, and we'll have specific labs dealing with them. Actually quite fun. These are flow control valves. What are a flow control valve? Flow control valves essentially do exactly what they say on the in the name. They control the flow of fluid of some sort. And the way they do that, I wish I could blow this up, but I cannot, is if you look, where did it go? There it is. So if you look, you have a what on this side? What kind of valve is that? It's a check valve. What does a check valve do? Allows flow in. It's a one direction flow, right? So if it allows flow in this direction, but not coming back, where does the flow coming back have to go through? It has to go through this right here, which is a constriction point. So, in other words, instead of allowing free flow through, it constricts the flow to the point where you have full control of how much exits that valve. Does that make sense? At least in the orientation it is put. Flow into this cylinder is not controlled. Flow out of it is. And we'll talk about the differences in that on another day. And if you look at this guy, the flow in is again controlled. The flow out is, the flow in is not controlled. The flow out is. This is actually a configuration called meter out. You will do this in lab one day, but that is in the future. And that's a different lab. We'll talk about it another day. All right, so what are my 4 valves on these 4 valves? What are they? First of all, how many ways do they have? They are 4-way. How many position? 2 position. So there are 4, 2. All right, what else can you tell me about them? The first one is a spring return. What else? They have 2 types of operation. What are they? What is the one on top? By that I mean this guy. What is that operator? The solenoid's the one at the bottom. The one on top is a what? Courtney? Take a look in your book, guys. What is that top operator? The bottom one's a solenoid. The top one is a what? Take a good look, guys. Which of those valves at the top of page 4 does that look most closely like? Personally, I think it looks like a general purpose. In other words, it's a push button or it's some sort of manual operation. Right? So not only does this have a solenoid function to it, but it has a manual operation as well. Okay? Y'all see that? Okay, so this is a 4-2 solenoid operated, manually operated spring return on this first one. And that pretty much tells you all you need to know about that valve, right? Any questions on those valves? Fairly easy once you hear it, right? I think these are the same thing, only a little more drawn out. Decided to be confusing about it. All right, so this is a 4-2-way solenoid operated with a manual override. I want to get a little more fancy with it. So in its normal operation, pressure comes in at 1, out at 2, through the flow control valve, and it goes into the cylinder to retract it. You'll see that? Following the red line. The air from the back of the cylinder comes out through the flow constriction and then comes back through 4 and out through the exhaust. You'll see that and how that works. The secondary way it works, so let's say it was shifted, the flow comes in at 1, goes through the flow control, comes out, and it forces the cylinder to extend. The air on the front side of this cylinder is going to come down, go through constriction, come in through 2, and go to tank, or go to exhaust, excuse me. Okay? Does it make sense to everybody? All right, so the last thing we'll kind of talk about again is some filters and dryers. So one of the biggest things we have with pneumatics is a filter trap, with filters with water traps. Why? Because what is the one thing that we have to suffer with here in Alabama in 90% of our life? That humidity, right? What is humidity? It's nothing but water in the air. What do we not want in any of our components? In anything mechanical? H2O, water. We do not like it. We do not want it. So thus we find ways to pull it away from what we're trying to do. And that thus causes us to need what are called water traps. If you look at the service unit to your individual trainers, you will see a clear bowl. That is your water trap. It's also your, yeah, that is your water trap. All it's doing is pulling water out of your air that is coming through your service unit, so it does not get into the rest of your components. Does that make sense? Some of these have automatic drains. Most of them do not. You have to unscrew it, and you have to pretty much have a trash can at hand so that you can drain the water into the trash can, not all over you. Okay? And we'll go ahead and tell you this. The water is not generally clean. It's got like rust and stuff in it, so yeah, you definitely want the trash can with it or something to catch all the nasty water as it comes out. These also can unscrew and you can dump the water out of them. But whenever you're doing that, make sure you lock out, tag out, and turn off any and all air to that service unit. Otherwise, when you start doing that, you're going to have air blasting at you at quite high speed. Okay? Everybody good? All right, so let's talk specifically hydraulics. Really not a whole lot different, except that these will have a center position, and there are 4 of them. Okay? If you want to see pictures of them, look at the bottom of page 3. So you have an open center, which means that flow is just suspended. You have a closed center, which means that pressure is maintained in all aspects of your set. You have the tandem center, which basically means all your pressure is just going to tank, so you can't build pressure at all. And then you have the float center, which means that you're holding pressure from from your pump, but all the pressure in your actuator is just drained out. There's nothing holding that in either way. Tandem means that you're pushing all your fluid to tank. You're basically running from pump to tank, just dumping everything out. You can't maintain pressure. Okay. So there, like I said, there really is no difference between these. The methods of operation are pretty much the same. The control elements, the number of control positions, and the number of connecting ports are all the same. The center position is what is really important with hydraulics, because they will tell you whether you're going to maintain pressure from your pump or whether you're going to drain pressure from your pump. Does that make sense? Okay. All right, so with a closed center, it means that you're doing what? Well, it means that you're going to hold pressure at all ports. Okay? If one port was drained, it will stay drained. If the other port and the other one should hold pressure. Okay? Your pump will maintain pressure. Okay? It's pretty much a really good illustration of it right here. So when the spool is centered, your pump cannot do anything. You cannot drain pressure from A or B, and your tank just is there. Does that make sense? Basically, everything closes off. If it's a closed center, it's like a closed door. Nothing's moving. Okay? Versus an open center. If you have an open center, everything's going to tank. Everything's draining. Okay? You're not maintaining pressure on anything. All pressure is not applied. Does it make sense? For a tandem center, it locks the actuator and the pump will vent. Okay? In other words, you cannot maintain pump pressure, but your actuator's not going to move. It's going to be locked in either the forward or the reverse position. The pressure will not be maintained. It's going to just go to tank. Well, let's put it this way. With hydraulics, everything goes to tank. Okay? That's just hydraulics. You don't pressure is something that is always carefully maintained with hydraulics, simply because pressure can be very dangerous with hydraulics. You get too much pressure accumulated in hydraulics, you're going to hurt something. Best way I can say that. Sort of like if you built up water pressure in something, let's say, I'll give you a good example. If you build up too much pressure in something like a water hose, or too much pressure, let's say you haven't cleaned your shower head in forever and you built up too much pressure behind it, what's going to happen? You're going to do what? Blow a seal or even bust a pipe. That's how pipes bust, is there's too much pressure maintained. So with any hydraulic system, I don't care if it's water or oil, you don't want to maintain excessive pressure because it wears out your components. It wears out everything. If you really want a good example, why do we not like high blood pressure in humans? It's because it wears out the walls of your veins and your arteries. Believe it or not. That's why they try and maintain a lesser blood pressure. It's less, you end up with less pressure in your heart, and you end up with less pressure in your overall veins and arteries. Too much pressure actually causes things to bust. It's the simplest way you can say that. So, I mean, the human body is probably the most efficient hydraulic system out there, and probably one of the best ways you can really think of a lot of this. So a float center. This is where the actuator does not maintain pressure. Everything just goes to tank, but your pump maintains the pressure coming through. Okay? Does that make sense? All right, and then you have some other conditions, but these are not as common. So you have one where you maintain pressure in your actuator. This is basically going to lock your actuator with the pressure of the pump. You have one where you close off your pressure and you close off the drain on one side and allow the other side to drain. This is another way of saying a tandem center, because your pressure is just going to tank and going to one side of your pump, and then you just have pressure maintained at A. There's a lot of different ways you can do this. The other ones are the main four. That would definitely make sure you know. Any questions, guys?